Hello guys, my name is Sophia Pao and I'm going to talk about nickel aluminum bronze. Contents, overview, application, alloying elements, microstructural phase diagram, property, corrosion resistance, heat treatment. Overview of nickel aluminum bronze. Broadly, the nickel aluminum bronze can be classified as alloys containing 6 to 10% aluminum and up to 7% iron and 7% nickel. The more common alloy normally contain 6 to 13% each of these elements. Manganese up to 1.5% is also added, both are antioxidant and strengthen element. Application: aerospace maintenance, marine defense, oil, gas, and petrochemical. Aerospace maintenance, landing gear bearing for the world fleet of commercial aircraft, the excellent bearing property against steel. Marine defenses, they are light market for naval application, particularly for submarine fleet of the world. The main applications are in seawater piping and valve system, weapon handling, flexible coupling, sonar equipment, seawater external hatch. Oil, gas, and petrochemical used as a pump valve and pump in seawater in pumping system, especially in firefighting equipment. Alloying elements. Influence of alloying elements. Aluminum is the main strengthening element and normally rank from 8 to 13% in this family of alloy. Manganese is added as a deoxidant, but also a major addition is important. Nickel is added in quantity ranging from 1 to 7% in conjunction with iron. It presents improve the corrosion resistance and increase the mechanical strength. Iron can define structure and provide toughness. Microstructural phase diagram. Above approximately 8% aluminum. A second phase known as beta appears in the metal structure at high temperature, which is stronger and harder. However, slow cooling below 565 degrees Celsius, the beta phase becomes unstable and decomposed to a finely divided structure, eutectoid, containing alpha and another stronger but less ductile, embrittling phase gamma 2. Gamma 2 can be attacked preferentially in seawater and it is not desirable. Nickel and iron addition. The gamma 2 as efficacy certified when both iron and nickel are present. At normally 5%, the structure of 9 to 10% aluminum alloy is modified, and instead of the formation of gamma 2 prime, a new phase kappa is created, which more beneficial. Mechanical strength. Nickel aluminum bronze offer a wide range of strength across a family of alloy. Table 7a. Increased aluminum content can improve strength in the sound. In table 7a, we compare case Copper aluminum 11 for 4 nickel 4 and copper aluminum 9 for 9 for 4 nickel 4 alloy with normally 11% and 9% respectively, with aluminum content above 10%. Very high mechanical property can be obtained from quench and temper heat treatment, but with lower ductility, and this also illustrates this type of alloy are mainly used in bearing application. Low and high temperature property. Unlike some steel, nickel, aluminum, bronze do not become brittle at low temperature and hence are ideal for cryogenic application down to -190 degrees Celsius. With decreasing temperature, there is gradual increase in proof and tensile strength and a fall in ductility and impact toughness, but not critical level. Table A. Fatigue strength. Most of work conducted On fatigue testing, all the nickel aluminum bronze has been carried out on rough alloy which are used under highly stressed conditions. The general active limited under reverse bending conditions for endurance in air at 10 power 7 cycle is approximately 300 to 500 Newton millimeters square, depend on the tensile strength. Grip strength in application of nickel aluminum bronze for pressure vessel desalination plants and condenser system, grip become important with elevated temperature in the range of 150 to 250 degrees Celsius. The design of this plant is normally based on 100K operational hour, approximately 12 years. Magnetic permeability. The magnetic permeability of the nickel aluminum bronze alloy is likely determined by the iron content and to a lesser extent the nickel content. The form of iron rich kappa phase and the way it precipitates also play an important role. Figure 41 illustrated the relationship between iron and magnetic permeability in an alloy containing 3.7% nickel. The magnetic permeability increased after approximately 1.5% iron. Corrosion resistance. The corrosion mechanism is mainly based on data and experience in seawater, but nickel aluminum bronze also has good corrosion resistance in many chemical environments. Pitting. Pitting can occur through a process termed differential aeration due to leucolide defect of the oxide or internal defect uncovered by machining or filtering. Pitting can also be caused by a technoball phase within the structure. Pitting corrosion in all metal is important consideration, particularly in thin wall components such as pipework, where because the localized nature of corrosion, perforation can occur. Nickel aluminum bronze has good resistance to pitting corrosion, particularly in rough conditions. Cathodic protection example, coupling to a less noble alloy can help reduce the risk of this type of corrosion, but has the advantage of suppressing the natural ability of this alloy to resist marine growth. Greaves corrosion. A greaves is a shell area are two component parts or foreign objects are in close contact with each other, allowing a thin film of liquid to penetrate between the two. It can be a thin film of water between flange and fastener, or a shell area which has resulted from marine growth or some other form of non-organic deposit. Greaves corrosion in metal is very complex mechanism and influenced by electrochemical reaction and Greaves geometry. This shielded area is style of oxygen and differential aeration take place, which create a potential difference between the oxygen deprived air and the external surface which may be richer in oxygen. Nickel aluminum bronze, which is not catholically protected or connected to galvanically less a noble alloy can be susceptible to Greaves. Heat treatment, stress relieving. This form of heat treatment is conducted to relieve internal stress which have been in use where cold working process assembly, stress rapid cooling matching or welding. The process is important for machining. Close tolerance are required or profile is complex as nickel. Aluminum bronze can have a tendency of spring after heavy metal remove wall or where there is a thin wall section such as aerospace bearing or sleeve. For removing machine stress, heat treatment can be conducted with between 300 to 400 or varying time depend on cross-section, and this has a little impact on mechanical property or microstructure. Annealing is normally conducted within a temperature range of 500 to 700 degrees Celsius, and as temperature increases within the range, microstructural phase change occur to a greater degree. Recrystallization will normally occur at temperature at 675 degrees Celsius and above, but may occur at low temperature where cold work or repeat cooling taken place. Table 22 shows the material which has been hot worked down to 650 degrees Celsius and finished cold, or a bar that has been extruded or rolling and then given a small degree of cold work can benefit from heat treatment within the range 500 to 600 degrees Celsius. Quenching and tempering. The copper aluminum nickel fur group react in similar manner to alloy to steel in response to heat treatment procedure, with martensite being formed when components are water quenched from elevated temperature within typical range 900 to 1050 degrees Celsius. With steel, the nickel aluminum bond one quench can be tempered to improve ductility while still retaining high tensile strength and hardness. Table 23, figure 52.